Okay, class, welcome to the first lecture. We'll begin by setting up some fundamental notation that we'll be using throughout the course. First, the set of the first n positive integers will be denoted as n within square brackets, which is the set containing 1, 2, all the way up to n. The set of all positive integers, also known as natural numbers, will be denoted by bold n, which is the set 1, 2, 3, and so on. The set of all integers, including negative numbers and 0, will be denoted by bold z, so that's -2, -1, 0, 1, 2, and so on. The set of non-negative integers, which starts from 0, will be bold z plus, meaning the set 0, 1, 2, and so on. The set of rational numbers will be denoted by bold q. The set of real numbers is bold r. And the set of non-negative real numbers is bold r plus. Finally, the power set of a set A, which is the set of all subsets of A, will be denoted as script P of A, defined as the set of all B, such that B is a subset of A. Now, let's talk about functions. For two sets A and B, a function from set B to set A is denoted as f colon B arrow A. This means that for every element B in B, there is a corresponding element f of B in A, forming pairs B, f of B, which are elements of the Cartesian product B cross A. Crucially, for each B in B, there is only one such value f of B in A. That is, the set of all pairs B, f of B for B in B is a subset of B cross A. In this setup, set B is called the domain of the function f. The set A is called the codomain of the function f. And the set f of B, which consists of all elements f of B in A, such that B is in B, is called the range of the function f. Let's consider an example. Let B be the set 1, 2, 3 and A be the set AB. The set of pairs 1A, 2A, 3B corresponds to a function f from B to A, where f of 1 equals f of 2, which equals A, and f of 3 equals B. We will often denote such a function by an ordered tuple, in this case AB. We have a special notation for the collection of all A-valued functions that have the domain B. This collection is denoted by A superscript B. So for our previous example, where B is the set 1, 2, 3 and A is the set A, B, the collection A superscript B is defined by the set of all possible ordered 3 tuples where each element comes from A. That is the set containing A, AA, AAB, ABA, ABB, BAA, BAB, BBA and BBB. Next, let's define the inverse map. For a function f in A superscript B, we define the set inverse map f inverse of C as the set of all elements B in B such that f of B is in C. This is defined for all subsets C that are part of A. It's important to note that this is a slight abuse of notation, as f inverse is actually a map from the power set of A, script P of A, to the power set of B, script P of B. It maps sets to sets. For instance, if B is the set 1, 2, 3A is the set A, B, and our function f is represented by the ordered tuple ABA, meaning f of 1 equals A, f of 2 equals B, f of 3 equals A. Then f inverse of the set A would be 1, 3. And f inverse of the set B would be 2. Now let's discuss some properties of functions. A function f in a superscript b is injective if for any two distinct elements b and c in b not equal to c, their images under f are also distinct. So f of b is not equal to f of c. A function is surjective if its range is equal to its codomain, meaning f of b equals a. And a function is bijective if it is both injective and surjective. Let's look at examples for these. For an injective function, let b be the set 1, 2, 3 and a be the set a, b, c, d. Then the function represented by the tuple a, b, c, meaning f of 1 equals a, f of 2 equals b, and f of 3 equals c, is an injective function as distinct elements in B map to distinct elements in A. For a surjective function, let B be the set 1, 2, 3, 4 and A be the set A, B, C. Then the function A, B, C, A, f of 1 equals A, f of 2 equals B, f of 3 equals C, and f of 4 equals A is a surjective function because every element in A is mapped to by at least one element in B. The range f of B is A, B, C, which is A. For a bijective function, let B be the set 1, 2, 3 and A be the set A, B, C. Then the function ABC is a bijective function because it is both injective, each element in B maps to a unique element in A, and surjective, every element in A is mapped to. Next, we'll talk about cardinality. We denote the cardinality of a set A by absolute A. Cardinality describes the relationship between sets that allows us to compare their relative sizes. If there exists a bijection between two sets, then they are said to have the same cardinality. Any set that is bijective to the set of the first n positive integers is said to have cardinality n. For example, the cardinality of the set A equals A, B, C is 3 because there is a bijection between the set B equals 1, 2, 3 and A. For instance, 1 map to A, 2 to B and 3 to C. Now let's define what we mean by a countable set. Any set that is bijective to a subset of the natural numbers n is called a countable set. If a set has a finite cardinality like n in the previous example, it's called a countably finite set. And any set that is bijective to the set of natural numbers n itself is called a countably infinite set. Here's a quick exercise for you to think about. Show that. First, the cardinality of a superscript b, the set of all functions from b to a, is equal to the cardinality of a raised to the power of the cardinality of b. Second, a superscript integer from 1 to n represents the set of all a-valued n-length sequences. Third, a superscript n is the set of all a-valued countably infinite sequences indexed by the set of natural numbers n. And fourth, the sets n of natural numbers, z plus non-negative integers, z of integers, and q of rational numbers all have the same cardinality. They are all countably infinite. Now we move to the core concepts for probability sample space. The set of all possible outcomes of a random experiment is called the sample space, and we will denote it by omega. Let's look at an example. A single coin toss. The outputs can be either heads, denoted H, or tails, denoted T. So the set of all possible outcomes, our sample space omega, is the set HT. Another example, finite coin tosses. Suppose we toss a single coin n times. In this case, the sample space omega is the set H, T superscript set of integers from 1 to n. A single outcome omega is then a sequence omega 1, omega 2, and so on till omega n. Each omega I is either H or T. Let's consider more examples of sample spaces. First, countably infinite coin tosses. If we consider an infinite sequence of coin tosses, the set of all possible outcomes, omega, is H, T superscript n. A single outcome, omega, is an infinite sequence, omega E, where omega E is in H, T for all I in n. Next, a point on the non-negative real line. If our experiment is to pick a single point from the non-negative real line, then the set of all possible outcomes, omega, is simply R plus. And finally, countable points on the non-negative real line. If the outcome is a sequence of points from the non-negative real line, then the set of all possible outcomes, omega, is R plus superscript n. A single outcome omega would be a sequence omega I, where omega I is in R plus for all I in n. Now that we have the sample space, let's define the event space. A collection of subsets of the sample space omega is called the event space if it forms a sigma algebra over the subsets of omega. We will denote the event space by script f. What properties must this collection script f satisfy to be a sigma algebra? First, the event space must include the certain event, omega itself. So omega must be an element of script f. Second, the event space must be closed under complements. This means that if a set A is in script f, then its complement A superscript C must also be in script f. Third, the event space must be closed under countable unions. That is, if we have a sequence of sets AI, where each AI is in script f for all I in n, then their union, the union over I in n of AI, must also be in script f. It's important to note that the elements of this event space script f are what we call events. Let's look at some examples of event spaces. The coarsest event space, for any sample space omega, the simplest possible event space is the trivial one, script f equals the empty set omega. You can verify that this satisfies the sigma algebra properties. For a single coin toss, recall omega was ht. We can define an event space script f as the empty set, the set H, the set T, and the set HT. I encourage you to verify that this script F is indeed a sigma algebra. For the finest event space in finite coin tosses, recall that for n coin tosses, omega was HT to the n. An event space for this sample space can be the power set of omega script f equals script p of omega, which is the set of all subsets A such that A is a subset of omega. Again, can you verify that this forms a sigma algebra? When omega is finite, its power set is always a valid sigma algebra. A remark on event spaces. We observe that script f is always a subset of the power set of omega. However, it's not always the case that all subsets of the sample space omega necessarily belong to the event space. That is, script f can be a strict subset of script p of omega. To show this, one would need to construct a set A that is a subset of omega but is not in script f. This becomes particularly relevant for uncountable sample spaces. Let's discuss some further properties of an event space an event space that contains the impossible event, the empty set, is closed under finite unions and is also closed under countable intersections. Let's prove these. First, the impossible event. Since the certain event omega is in script f and script f is closed under complements, the complement of omega, which is the empty set, must also be in script f. Next, closure under finite unions. We need to show that if A and B are in script f, then their union A union B is also in script f. This follows from the closure under countable unions. We can define a sequence A1 equals A, A2 equals B, and AI equals the empty set for all I greater than or equal to 3. Since the empty set is in script f, this is a countable sequence of sets from script f, and their union is A union B, which therefore must be in script f. Continuing the proof of properties, we also need to show closure under countable intersections. That is, for any sequence of events AI such that each AI is in script f for all I in n, their intersection, the intersection over I in n of AI, must also be in script f. To show this, we first note that since each AI is in script f, its complement AI superscript C is also in script f due to closure under complements. Then by closure under countable unions, the union over I in n of A, I superscript C, is in script f. Finally, the result follows by taking the complement of this union, which by De Morgan's laws is the intersection of the AIs, and using the closure under complements property again. So the intersection is indeed in script f. Now let's define the event space generated by a family of sets. Consider a sample space omega and a family f, which is a collection of subsets of omega. So f is a subset of the power set of omega. Then the event space generated by f, denoted by sigma of f, is defined as the smallest event space that contains every element of f. As an example, consider the event space generated by a single event. For any sample space, omega and a single subset A of omega, the smallest event space generated by this event A is script f equals the empty set A complement omega. Let's look at another example. Returning to countably infinite coin tosses, recall omega is ht superscript n. We aim to construct an event space script f on this outcome space that is not the power set of omega, which is actually unmanageably large for this case. By definition, any event space must contain the certain event omega and the impossible event empty set. Let's consider the event space script f generated by a specific sequence of events an. We define an as the set of all outcomes omega in omega, such that omega I equals h for at least one I within the first n tosses. This is for each n in n. So an is the event of getting at least one head in the first n tosses. We can see that the sequence n for n in n is a sequence of increasing events. A1 is a subset of A2 and so on. From the closure property under countable unions, the union over n in n of an must be in script f. This union is the event of getting at least one head eventually, which is omega minus the sequence made up of only t's. Here's an exercise for you. Consider a countably infinite sequence of coin tosses with sample space omega equals ht superscript n, and the event space script f generated by the events an as defined in equation 1 event of at least one head in the first n tosses. let Bn be the event of observing the first head on the n-th toss. Show that Bn is in script f for all n in n. Now, let's define Borel event spaces. For the sample space R, the set of real numbers, a Borel event space denoted script B of R is the sigma algebra generated by all subsets of the form Bx, where Bx is the interval from minus infinity to x inclusive for every x in R. So, script B of R is sigma of the set of all Bx for x in R. As a task, show that the following events belong to this Borel event space script B of R for all x, y in R, the singleton set x, the open interval from x to y, and the closed interval from x to y. Let's walk through the solution for showing these sets are in script B of R. Let x, y be in R with x lesser than y. We want to show that x, open interval from x to y, and closed interval from x to y are in script B of R. First, we observe that since the interval from minus infinity to x closed is in script B of R by definition as a generator, its complement, which is the open interval x infinity, must also be in script B of R. Similarly, open interval I infinity is in script B of R. It then follows that the intersection of open interval x infinity and interval from minus infinity to y closed, which is the interval open from x to y closed, is in script B of R since sigma algebras are closed under countable and thus finite intersections. Now consider a decreasing sequence un that converges down to x and an increasing sequence ln that converges up to x. We observe that for each n, the interval from minus infinity to ln closed is in script B of R. By closure under countable unions, the union over n in n of interval from minus infinity to ln closed is equal to the open interval minus infinity x, and this must be in script B of R. Therefore, it follows that the closed interval x comma y, which can be written as the intersection of the open interval minus infinity to x complement and the open interval from minus infinity to y closed, is in script B of R. We can similarly show that open interval from minus infinity to is in script B of R. Then it follows that the open interval from xy, which is the intersection of interval open from minus infinity to x closed complement and open interval from minus infinity to y, is also in script B of R. Finally, we observe that for each n, the singleton set x is contained in the closed interval ln, un. Each of these closed intervals ln, un can be shown to be in script B of reg, closed interval ln, un equals interval from minus infinity to un, closed intersect interval closed from ln to infinity. The singleton set x can then be written as the countable intersection over n in n of the closed interval ln un. Since script B of R is closed under countable intersections, x must be in script B of R. This concludes our first lecture covering basic notation, functions, and the fundamental concepts of sample and event spaces.